To end this section, we're going to take a look at just two final quick examples, examples 10 and 11. These are just going to ask us to use these inverse trig derivative rules to actually calculate some different derivatives. Let's take a look here at example 10. I want to try to find the first derivative of the function y is equal to 1 over the inverse cosine of x. Now it's important for me to note here right off the bat that there are some relationships that may seem like they are going to work in inverse trig functions, but they actually do not. And so if I was to go ahead or I should go ahead and note the following. Something like 1 over the inverse cosine of x is actually not the same as the inverse secant. I do not have reciprocal relationships here. It's actually the case that the inverse cosine of x is equal to the inverse secant of 1 over x. And so the change of the reciprocal actually happens on the inputs of these inverse trig functions. So I got to be careful first not to try to just rewrite this as inverse secant and state this derivative. Instead, what I could do is to note the following. I'm going to go ahead and say that I'm going to rewrite y as the inverse cosine of x being raised to the negative first power. And the reason I'm going to do this is that I'm going to try to avoid using the quotient rule to take this derivative and instead deal with a chain rule. So now when I compute y prime, I can take -1 and bring it to the front. I can then lower my power to -2, and then I can just multiply by the derivative of the inverse cosine, which according to what I have up here is -1 over the square root of 1 minus x squared. Now of course I could simplify some things down here. I can see that my -1 times this other -1 are going to result in a positive amount. So ultimately I'm just going to have 1, and I'm going to have an inverse cosine of y down here, and then a square root of 1 minus x squared. And so this right here is actually the derivative. It's a little bit messy, but that's what I end up with. Now let's take a look at here example number 11. I'm going to try to take the derivative here of the function inverse tangent of the square root of x. Now this is really important because what you'll notice here is that I have actually included a composition of functions here, right? I have the square root of x function being plugged into the inverse tangent. And it's really important to see what exactly it is we're supposed to do in scenarios like this. So if I wanted to start to take this derivative, I would see that first I would go ahead and note what the derivative of the inverse tangent function is, right? Because I'm going to have to use the chain rule here. So the derivative of the tangent, the inverse tangent of something, and so I'm going to kind of blot out that x for the moment, but the inverse tangent of red stuff is always equal to 1 over 1 plus red stuff being squared. So if I have something more complicated than just an x, I'm still going to put it in the same spot that x used to be in this derivative, and then I'll use the chain rule to take the derivative of that red stuff after. So in this case, I would get, I would end up with 1 over 1 plus stuff being squared, and then I would multiply on by the derivative of that stuff, which would look like 1/2 x to the -1/2. I'd just use the power rule for that piece. So if I was to simplify this down a little bit, I would notice that this is going to be 1 over 1 plus x times 1 over 2 square root x. Or if I wanted to write this kind of all together in one fraction, I could write like 2 square root x and then 1 plus x. Right, so here's my derivative. But this portion right here in red is really the most important portion to keep in mind. That when I have a composition, I need to go ahead and replace that stuff that's on the inside of the inverse tangent or the inverse sine, and I need to put it in place here. So imagine the same thing happening with the inverse sine function. If I had the inverse sine of e to the x and I wanted to take its derivative, I would have to put e to the x right in here, and then take the derivative of e to the x after. So hopefully this gives you a good sense of how you can use these inverse trig derivatives, and of course you can go ahead and practice some of these concepts in the associated worksheets.